Hi, good evening, everyone. This is what, video 6, I believe. I can check real fast here. Come on, CMA. Video 6. Yes, no. Near algebra. This is video 5. Since I didn't make you watch this, well, today, Monday, because it's a holiday, I made it for homework. So you should have watched this before Wednesday's class on the 9th. Okay, and so let's just jump right into this because I've been going over this for a while. So this is theorem 10 in the book. So we're going to let T be a linear transformation from Rn to Rm. Then there exists a unique matrix A such that T sub x equals A sub x for all x in Rn. Now this is a big theorem, and one we use all semester long because it brings into conversation a big deal in mathematics. And that's the idea of existence and uniqueness. And this theorem has both. And what this whole section is about is sort of some small ideas that have a really big overlying consequence, basically. And this theorem runs the whole show. It's an existence and uniqueness theorem. Some theorems are existence only, some are uniqueness only, and sometimes you get one like this where it's existence and uniqueness. Okay. So all this is saying is that if you give me some linear transformation from Rn to Rm, doesn't matter what it is, there's a matrix out there, a unique one, that defines the transformation. And so most of our goal is finding this thing, which usually isn't a big deal, okay? And then we throw in a definition. The mapping T defined above there is said to be onto Rm if each vector B in Rm is the image of at least one vector x in R. And there might be more than one, but there has to be at least one. So this is an existence definition. And well, you can't talk about onto-ness without talking about the other definition, which is one-to-one. So the mapping T is 1 to 1. If each vector B in Rm is the image of at most one x in Rn. At most one. So this is a uniqueness. And the best mappings, the best linear transformations are ones that are one-to-one and onto. Okay. So let's look at some examples here and try and get a handle on this definition and this one. Okay. So Here's an example 1. So we're going to let A be the matrix 1 minus 4, 8, 1, 0, 2, minus 1, 3, 0, 0, 0, 5. Sure I wrote this down right. 1 minus 4, 8, 1, 0, 2, minus 1, 3, 0, 0, 0, 5. Does T map R4 onto R3? That's question 1. And is T 1 to 1? That's question 2. Okay, first of all, so here's our solution. Well, note, A is in echelon form. If you wanted to, you could make it into row reduced echelon form, but we don't need that. We just look at it and say, well, it's an echelon form. There is a pivot position in every row, right? In row 1, there's this guy. In row 2, there's that guy. In row 3, there's that guy. So by theorem 4 in section 1.4, for every B in R3, AX equals B has a solution. It's consistent. This is theorem chasing, right? So that says T is onto R3. Now this really needs to marinate for a second, okay? So what we're trying to show here, using the definition of onto-ness, if you give me any B in Rm, which in this case is R3, is there at least one X in Rn that maps to it? Back here, using theorem 4, this says, well, since A is an echelon form and there's a pivot position in every row, by theorem 4, for every B in R3, there is at least one solution to this thing. There might be a bunch. It could be infinitely many or 2 or something, but there's at least one. So one exists. And this says that T is onto. Okay, however, since the equation AX equals B has a free variable, namely what? Well, you see this vector matrix? Pivot, pivot, pivot. No, so since AX equals has a free variable, in this case, X3 is free. Each B in R3 is the image of a bunch of X. It's real mathy in R4, okay? And so I'm going to stop the video here and say, all right, so we don't have to do this, so we're done. We've shown that it's onto, but not one-to-one, okay? Because there's more than one that maps to it, right? Whereas this one-to-one definition says there has to be at most one. And down here we're saying there's a bunch more than one. In fact, there's infinitely many. So let's take a moment here and find the solutions. To AX equals B. And I mean, you can just pick any old B you want. I don't know, why don't you let B be 0, just for fun. That's you know, because it has to be for all of them, so you might as well pick one of them. And the easiest one to pick is 0. So Find the solution to ax equals 0, and then come back and we'll talk about this. Okay, we're back. And hopefully you did the work and saw that the vector x that maps to the 0 vector is any multiple of -6, 1/2, 1, 0. Right? And that's not what I asked for in this problem, but I just wanted to show you what the hell I'm talking about. This says that if you're going under the definition of 1 to 1, and you take some x in Rn, it's supposed to be true for every x, so if you just pick one and you show it's not true, then you've disproven it. So we just chose our vector b to be 0, because that's easy to work with. We row reduced the, what was already row reduced. We just solved the echelon form and came up with this general solution with one free variable x3. So that says much more than one vector maps to 0. A bunch of them do. Any multiple of this vector does. So t is, we showed t is onto, but it's not 1 to 1. Now this is one of those examples. It would be cool. I'm going to assign a problem or problems just like it, but because I've done it this way, it would be cool if you just did it again on your own and said, all right, let me do this from scratch. Let me really read the definitions and see if I can't reproduce this and mostly understand it, because we're going to talk about this at length. Okay, so now we move on to another theorem. This is a great theorem. Okay. So let T be the linear transformation Rm to Rm. Right. Then T of x is 1 to 1 if and only if, which in math we write like this, arrows going in both directions. So if and only if the equation T of x equals 0 has only the trivial solution. So to really go, if we go back up here and use this theorem now, when we started this, what we'd say is, oh, by theorem 4, since every b in R3 has a solution, T is onto. And then we'd say, from this work, since ax equals 0, it doesn't have the trivial solution as its only solution. By theorem 11, it's not 1 to 1. And that's the kind of language we need to start having in this course. It's really what linear algebra is all about. And like, you see so little math on this page because it's all about understanding how these theorems work and how to apply them as tools. Okay. All right, I went a little out of order from your book because I get what Lei was trying to get at, but I like this sort of direction. I took it in a little different. Okay. So going back to theorem 10, there's a corollary. I had a British instructor in college who called it a corollary, and that's still how I want to say it every time because we were kind of making fun of him, but now it's sort of stuck. Okay. So, wow, there's so many sirens today. Okay. So we're going to let A be the m by n matrix whose jth column is T of E sub j, where E sub j, the vector E sub j, is this. It's all zeros with a 1 in the jth position. And your book says it's the columns of the identity matrix, which is true, but we're really building up to something much bigger than that. And so I'm gonna make it be this way. So let's say, so for example, I'm gonna make a big deal out of this. Let's say A is, let's see here. A is a 3x3 matrix, right? And so in this notation, E1 is the vector 1, 0, 0. E2 is the vector 0, 1, 0. And E3 is the vector 0, 0, 1, right? So the jth position here is 1, the first position. The jth position here is 2, so like that. So this is leading up to bases, which is another big deal in this course. And so, anyways, so we're gonna lay A be the m by n matrix whose jth column is this thing, T of E sub j, where E sub j is this column vector with a 1 in the jth position. Right. Then A is the mappings of T on this. So it's T of E1, T of E2 dot dot dot, T of En. And this gives well, it's a map. Oh, it's so hard to hold my hands tied because in 2 weeks when I really explain what's going on here, it'll be completely clear. But for now, this is it. So for every one of these linear transformations from Rn to Rm, A turns out to be an m by n matrix whose jth column is T of Ej, where Ej is this thing. And we write A in column form like this. And then now we can talk about what your book labels as theorem 12, which sort of summarizes what we've done in this section, all right? So let T take Rn to Rm. And let A be this matrix TE1 down to TEN. Okay. Right. Which your book calls the standard matrix for T. And I will be using that for this theorem, and then in the future we'll ditch this and we'll make it much better. Okay. So A, T is onto, it's an onto mapping from Rn to Rm, if and only if the columns of A span the image Rm, and B, T is 1 to 1, if and only if the columns of A are linearly independent. Excuse me. And so this is a big deal for us. These two solutions, and again, this part is just notation. We'll change it in a minute here, but this is what you want to use when you're doing homework, right? This mapping is onto if the columns of A span Rm, and if you look at theorem 4 from 1.4, there's a whole bunch of, there's 4 more parts of that theorem that talk about spanning, and then T is 1 to 1, and only if the columns there are linearly independent, which in a minute will tie into determinants in 3x3s. Or n by n, so. All right, that's all I got for now. I gotta go get my laundry. Okay, this is homework 3, which is due Monday the 14th at whatever I normally make at 2 p.m., 1500. And your assigned problems 2, 6, 14, 28. I thought I had one more on there. 29 and 30. The language is a little weird, so I'm going to do problem 1 to model 2 and 6, and then 14, 28 are linked, so that won't be too bad. So 2, 6, 14, 28, 29, 30, and now I'm gonna do problem 1. I'm gonna do problem 1. Okay, so this is section 1.9, problem 1, which says T is a mapping from R2 to R4, and T acts on E1 and gives you the vector 3, 1, 3, 1, and it acts on E2 and gives you the vector -5, 2, 0, 0. And then they say, all right, well, E1 is 1, 0, and E2 is 0, 1, right? So it's implied that E1 is the vector with 1 in the jth position and 0 is elsewhere. In this case, we're in R2, so it's going to be 1, 0, and 0, 1. And then it says, all right, find A, such that T of x equals AX. So where A is what they're calling the standard matrix of T. Okay. Well, by whatever theorem, it's called theorem 10, A is just 3, 1, 3, 1 -5, 2, 0, 0. That was hard. It's so easy. It makes me insecure. I'm trying to find that other theorem. It's not in here. And that's it. Pretty easy. Okay, well, since I got your attention, let's call this problem 1.9 dash. I'm going to add some stuff here. Is T onto? Is it 1 to 1? Right? So, like most things in this course, if you start off by finding the row-reduced echelon form of a matrix that you're working with, whatever you're doing with it, it's probably the right first step. So this has got 4 rows and 2 columns. Rows 3 minus 5, 1, 2, 3, 0, 1, 0. Okay. The row-reduced echelon form of A is 1, 0, 0, 1, 0, 0, 0, 0. All right, so the question is it onto R4? And is it 1 to 1? So here's questions. How many pivot positions are there with respect to the rows? How many free variables? Okay. So when I see you Wednesday at 2 p.m., that would be 9, 9. I want answers. Is T 1 to 1? Is it onto? And if so, why?